So be sure to memorize your new derivative rules. Memorize the new derivative rules with their respective domains. I do need to make a correction here. This one should say negative infinity to 0 union 0 to infinity. We can't include 0 there. The function is not defined at x equals 0. So once you have these properties, or once you have these rules of differentiation memorized, with their respective domains, hopefully taking derivatives and expanding your knowledge of functions become a lot easier. You should have already memorized the product rule, but this is a reminder of how I perform the product rule. I like to differentiate right away, so I actually differentiate the first function in the product. So let's go ahead and find a derivative function for each of these. If you want to, you could try to practice this on your own. This would be a good time to pause the video and try to exercise your Leibniz notation and your prime notation. Once you've given yourself an opportunity, go ahead and unpause the video to check your answers. We're going to differentiate y with respect to x. So really, we're just simplifying an expression here. And remember, once you do your Leibniz notation, make sure you remember your function notation or your prime notation. You want to make use of factoring. Factoring is a key procedure in calculus, especially when we're going to find critical numbers later on using the first derivative. This particular example, you got to recognize to make use of the chain rule. We'll begin with Leibniz notation. So remember, the chain rule says you take the derivative of the outside function evaluated at the inside function. So the derivative of the outside function is actually the natural log, all right? You might call it the natural log of u if you wanted to. And then you got to make sure you back substitute your u function back in, and then go ahead and take the derivative of your u function. The derivative of your u function is actually the square of cosine of x. And that requires a chain rule. And from trigonometry, you know that's the opposite of sine of 2x. All right. Well, we'll put it right here. Ready to write our function notation. And trigonometry allows you to write this in a few different forms. And they're all equivalent. That's what's mind-blowing. Yeah, so either one of these are acceptable. I gotta remember the number here. That's better. If you can't read that, that is actually a -2. Continuing on with more practice, once again, you could pause the video and try this yourself. And then once you give it a try, double check your Leibniz notation and your prime notation to see if you are actually doing these things correctly and precisely. This example here requires the product rule. A reminder, that's how I perform my product rule. I like to differentiate right away. Now, when you differentiate this, you do need to remember the chain rule. So this -1 will conclude the chain rule there. And derivative sine of x is simply cosine of x. Ready to simplify this and write this in prime notation. For example 9 and 10, we'll go ahead and use logarithmic differentiation to find y prime of x. Let's begin with using the natural log function. Now you got to remember y is some function of x, so if we need to, we will actually implicit differentiate. And we'll go ahead and implicit differentiate both sides of this equation. And notice the right-hand side is going to yield the product rule for differentiation. If you want to attempt example 10 on your own, simply pause the video and try it yourself. And when you need to check your answer, go ahead and unpause the video. Remember that y is some function of x. So when you implicit differentiate, you get 1 over y times dy dx. The power of Leibniz notation. The right-hand side of this equation is simply the product rule.